Hello, everyone. I've got to bring on the flamingo because we're talking about animals and stuff. Cool. Everyone. So yeah, you might be asking what a taxonomic equivalence engine is. It's a bit of a mouthful, but it's a knowledge graph, so we'll get to that. And yeah, Siobhan and I are going to talk a little bit about the work we did with the Natural History Museum, a bit of last year and a bit of this year as well. And a bit of a fun fact. So prior to getting involved in data and things like that, we're both biological scientists in another life, which was kind of relevant for this project and helped have a bit of a domain understanding. Can everyone hear me okay? Perfect. All right, let's try and get this show on the road. Cool. So taxonomic what? We're going to come to that. But essentially, naming things is hard. And how do you know if, two objects in different databases are referring to the same thing or not? That's kind of broadly the problem we're trying to address in this specific case. Just to get everyone on the same page to begin with, just introduce the Natural History Museum, the problem space, and why should you care, or why we cared at the time as well, and then how we went about building the solution, and then what business value the client got, but also maybe more broadly, things we learn, and also particular aspects where a solution like this might be good. Okay. Oops, that's the wrong way. Okay, cool. So Natural History Museum. Just so everyone's on the same page, in the UK, the Natural History Museum is pretty famous for like dinosaurs and things like that. And it has over 5 million visitors a year. So it's like a pretty big tourist attraction in South Kensington, just down the road from Harrods. So always massive queues during school time and things like that. But it's got over 80 million objects there, going back billions of years, from like meteorites that hit the Earth and things like that. Maybe even some stuffed flamingos. But it's also a very active research hub. And scientists at the Natural History Museum basically study the natural world and everything that covers. Plants, animals, even microorganisms you can't see, like bacteria and viruses and the like. And the way they do that is by, classifying and identifying species based on shared characteristics. So a bit of taxonomy 101, shared characteristics of vehicles, for example. Like if you are a road vehicle, you're going to have maybe tires and wheels that touch the ground. Motorbikes may just have 2. Other vehicles might have 4. And aircrafts, all have wings and things like that. So that's kind of your vehicle hierarchy. And then, if we kind of move into the world of, plants and animals and other things, you can start off with a very broad category at the top, go down to, say, the kingdom of animals, and you keep going to mammals, and you progressively get less and less things in there. Now, if you know your Latin or your constellations, obviously Ursus Major and Ursa Minor, a little bear or greater bear and lesser bear. And the Ursidae family, which is this one here, the third one, is all the bears, basically. And then if you get to the genus, which is just below that, you have Ursus, and that's a few less bears. That includes things like polar bears, brown bears, and American black bears, which is a species. And so this has a scientific name, Ursus americanus, but, more commonly known as the American black bear. So this is kind of like the classification in taxonomy that we were working with. Our list can be kind of shown a bit like that. So you've got your family at the top, and then it splits with different shared characteristics, getting more specific down with Ursus americanus at the bottom. And we're going to stick with this example through the top. Cool. And so that's how they might classify and follow species. But just around the gardens in central London, they've got this big wildlife garden, and they've been following and tracking species over the last 30 years. And Martin just was speaking about, the donuts of Kate Raworth's donut economics, and one of the things was biodiversity loss. And what the scientists here, they've been tracking long-term biodiversity using the amounts of species in different habitats and things like that. And so in the gardens alone, they've identified over 3,000 species, which is pretty cool for such a small area. And yeah, so the key thing that they're looking at the moment is urban biodiversity and how that can, help us track and make changes for basically humanity, which is pretty cool. And they've got various ways of identifying species. You can go around and spot things and visual observations. Oh, that's a butterfly or a bird. They've got these cool audio moths, they're called, which can listen out to various animals and species, and then use ML or expert knowledge to identify species that way. But the one we were most interested in for this kind of talk was the DNA barcoding. What they do is they take water samples or soil samples, even from air sometimes, and they can send it to the lab, various processes come back, and unique signatures for each species can identify the species, a bit like CSI, but for plants and animals and microorganisms, which is pretty cool. And so what the scientists do is they kind of get all these soil samples, but unlike when you spot a bird, it's one bird or a flock of birds, in these individual samples, it can contain hundreds or thousands of even species. And so there's like lots of things that they have to deal with. So it's not like you just spot one bear and like, oh, that's a bear. There's loads of bacteria and viruses and the like. And so what the scientists kind of wanted to do and how we tried to help them was they want to bring together all these different types of observations into this kind of data portal that we're also building for them as part of a wider project, so that no matter where the observation came from, be it DNA, acoustics, or visual, they could kind of identify the species and track biodiversity more broadly across both the UK and, the world. Blah. All right.
This is me. Oh, that's very loud. Okay, so what problem are we actually trying to solve? So apparently there are only two hard things in computer science: cache invalidation and naming things. And thankfully, I'm not working on cache invalidation. We're working on naming things is hard. And here's an example that you can maybe visualize, take from main data management. Is how do you know if two objects in different systems are referring to the same thing? So Andy Symonds from the UK, is that the same person or object as Andrew C.E. Symonds in London? And it's not just in computer science that naming things is hard, even within the English language itself. So we have the classic in the, wrong one. In the UK, we call this football. We call this football. In America, they call it soccer. We call this a car boot, and it's a trunk in America. We got biscuits and cookies, and then we got one that maybe more people can understand. We call this crisps, but I think everybody else calls them chips. So how do you know you're talking about the same thing and not some actual fish and chips? And so this is where this problem comes into this data ecosystem. Visual observations and acoustic observations that the NHM researchers or other people in the UK make, they use what we call the UK taxonomy naming standard. But for DNA barcoding, to identify species from a sequence of DNA, this uses an application which is based in America, and that uses the US taxonomy naming standard. And so basically, naming things is hard. And how do we know between the US and the UK naming standards if two objects are referring to the same thing? So it's basically just two different databases. So here's our problem statement. Identify species from DNA uses the US taxonomy database, and these need to be equivalenced into the UK naming standard. Equivalence is required because the researchers, they want to be able to not just compare observations from different sources, but even just combine them to get a richer knowledge of the biodiversity. Again, as Andy said, you get thousands of species identified in a single sample. So actually equivalencing between the two can be quite manual and slow. And also there's a case where there's not necessarily a direct species match from the US to the UK, which we'll explain later. So this is where the taxonomic equivalence engine comes in. As we said, it's basically two different taxonomy naming systems, two different classification systems, which can be considered two different databases, one in the US and one in the UK.
Cool. And we decided to solve this problem using a knowledge graph. And essentially, just so we're all on the same page, because knowledge graphs can have kind of different meanings to different people. For the purpose of this, it's a network of facts connected by explicitly defined relationships. And from that, you can infer new knowledge and new links across the graph. And often there's an underlying schema or structure, and it's known as an ontology. And so the nice thing about this taxonomy hierarchy is we could represent it as a graph structure. So the only difference here is that we've got, edges labeled as the relationships between the various taxon levels here, and then the nodes are the actual entities themselves. And so, for example, would be an organizational hierarchy where, you've got the regions, and if you focus in on the Europe region, there'll be maybe service lines within here, like the data and AI service line, of which you've got staff members like Andy and Siobhan. Please, yeah.
These taxonomy, the species we want to do come from that.
Yeah.
Why are they different from British and
Great question. So historically, and Siobhan might touch on this a bit later as well, historically the UK naming standard has been built from visual observations, and the new kind of techniques of DNA barcoding have come along a bit later, and they've just organically been created without necessarily full taxonomic input. It's just whoever's found sequences, names, and put them in, and that's broadly happened in the US. And so there's these sequence alignment tools where you have your sequences of DNA and you align it and match them all up, and that's all done from a US database essentially. So, but also you might have gaps in the UK, and so it's not just the equivalenting, which we'll get to, it's all about finding where gaps in your knowledge is as well. Don't know if you want to add.
Oh, I was actually going to say that as the researchers do more research, they sometimes change the names of the species. So you have older names that move forward, and the two different systems will not necessarily pick the exact same version of that name to be the official scientific name. So you get basically a lot of synonyms, and Andy's going to talk about that as well.
So for polar bears and black bears, it's not too much of a problem. But for bacteria, people get quite, dogmatic about what this bacteria is called. We can't control that. So it's a human problem. So yeah. Great. And so we built a taxonomy database with a software called TypeDB. And this is from their website, a polymorphic database. You can have lots of different types of data in there. And the data model is essentially a ball and stick that you might draw for a graph. You can represent it and save it in that database. And it's got quite a powerful symbolic reasoning engine, so you can infer knowledge across the graph too, which we'll speak to as well. And essentially, entities are essentially the nodes, which we'll represent as these like pink triangles. Not sure if it comes across as pink there. Edges are the relationships. And actually, as a side note, the nice thing here is, unlike other graph databases where you have a pair of nodes connected by an edge, this database allows kind of called a hypergraph, but you can connect a set of nodes with an edge as well. So you can connect many things together, and that can help. And then they all have attributes that you can give, which we'll see in a second. So just going to go through and show what this would look like for taxonomy. So this was our kind of example here. We've got the organizational hierarchy on the left and the taxonomic hierarchy on the right. And so, just change the code here. So now we've got these taxon levels here, and that's the taxon name entity as you go through. And then we can layer on top of that the relationships here. So this is where the orange diamond comes in. The nice thing about this is that within a relationship, the entities on either end of that relationship can play a role. And this is how we represented the hierarchy. So you knew what was higher up and lower down the hierarchy, because we had, on the right here, this family plays a superior role in this relationship, and the genus, which is below it in the hierarchy, plays a subordinate role. So you can attach that to it. And then on top of that, we can add, there we go. We can add attributes. So now we're just showing the right-hand side of the hierarchy here, but then the attribute of name for the family has Ursidae, which is the bears, and then you have a rank attribute, which in this case family, and you can go down all the way to species. So this is, your name is now the scientific name of Ursus americanus, and then it has the rank of species. And in fact, we had to have loads more attributes because scientists like to record more things as well. And so now I'm just going to focus in on how we modeled the two different databases, the American and the UK, by just focusing in on the species level of things, although we did have the whole tree in the graph. And so if we now go to how we modeled the American species, what we had is we got the taxon name entity, and in the kind of US database, all names, so both the scientific name and common name or any other synonyms, are all attached to the same entity, and they're given the same ID. And so that's pretty simple. Everything just goes onto the one entity. But in the UK, they like to do things a little different. And so what happens is the Ursus americanus, so their scientific name, was connected to one entity with one unique ID. And then the black bear or any other synonym, and there can be many synonyms for loads of names, especially bacteria, that would be connected to an entity with a different ID. And so the way we dealt with that is we connected them via a relationship, which we called concept description. And the roles that you can play within this relationship was there would be the synonym role here and also the recommended name. And I mentioned that you could have many things in a relationship here. So if there's many synonyms, they could all be connected with this concept description back to the proper scientific name, which was the recommended name. And so what we were able to do using this is we could take the US database and the UK database and put them all into and load them into this graph. So they were all contained within there in TypeDB, which was helpful. And finally, this is, I don't know if that's really come across, but this is like a snapshot of what the schema looks like. So you can view the schema like a graph too. And so a few things to point out is here, this is a taxonomic hierarchy relationship. And probably can't see, but these are like, one of them says superior and one is subordinate. And then the concept description relationship here. And so they kind of loop back onto the taxon name entity. But then as you go up and down the graph, the attribute of rank will change from, family, genus, and then down to species. So that's how that looks like.
Okay, right. Now, so that basically all the data has been modeled and we've got the two taxonomy sort of graphs into a single knowledge graph, we can actually begin equivalencing between the two. We'll start first of all with like the most simple match, which is just direct matching. So here we have the taxon name entity from the US. And if we get from the DNA barcoding, if the output of the identification of the species is Ursus americanus, then we can take advantage of the fact that in TypeDB, these attributes are globally unique. So there's only one name attribute called Ursus americanus, which links these two taxon name entities. So you get like a direct link between the two knowledge graphs automatically just from data modeling. And then you can basically retrieve the UK attributes of like the ID. This is the recommended scientific name. But what about if you got an input name, which was a synonym? So here we're using the common name, black bear, but typically it would be basically another version of the scientific name. So this is Ursus americanus, something like Ursus americana or something has been historically used. So if the DNA sequencing produces basically what the UK considers a synonym, but the US considers a scientific name, that is also globally unique. And so these two entities are still linked. But this is obviously linked to the entity with the UK ID, which says this is not a recommended name. This is a synonym. But because of the concept description relationship, you can then just traverse this relationship and retrieve like the correct name, ID, and it's the recommended scientific. Okay, so that's the simple version. The next one, we're going to use basically inference to infer new knowledge across the graphs. And why would we want to do this? So basically, we want to find new links between the two knowledge graphs because there is a case where the species do not have a direct match in the UK database. And this can be illustrated here. So in the US, you have like the bears, you have their full sort of taxonomy here all the way down to species. But what happens if these species, this data, does not exist here? Did I do something? Oh. Does not exist here in the UK. For that match, you want to return the genus Ursus, the closest node match. So basically, you want to go up the hierarchy to the very next level where you have this unique direct name match, which is Ursus. And to do closest node matching, you can basically use rules. So in this, back to our schema where you have the entities, the attributes, and the relationships. But within the schema, you can also write rules. And these rules are then used at query time to infer new knowledge across the graph. The rules can be used to create these new attributes or new relationships, but these only exist at query time, so they're not written back into the database. And so we have sort of a series of 3 rules, but the first rule is basically a pair of rules called the red match and the green match rule. The green match is probably the easiest to understand. So between the US and the UK entities, if there's that direct link, that unique name attribute that links the two, we're going to call it a green match. Whereas if you don't have a green match, you don't have any direct links. We're going to tag it as a red match. The next rule then is a graph traversal rule, which is based on the transitive closure of a graph, which can be illustrated here. So if you have this node A connected to B, B is connected to C, A has a path to C. So A is connected to B. And now if A is connected, A is connected to C. And now if A is connected to C, C is connected to D, A is also connected to D. And this is basically a recursive traversal of a graph. So you can go all the way from A to E, or as in this case, you go from species all the way to like the very, very top animals and higher. And it just basically recurses up to the top of the tree. So our rule basically is called the red path rule. So it restricts the recursion to only the red nodes. The red path rule will create these little relationships between red nodes that you can traverse up them, but there's no relationship between a red node the minute you get to a green node. So you're getting to basically the first match. And then the final rule just creates this relation from your input species. It connects it to the closest node, which is on the UK tree. And putting all these rules together, it means you can just write this one simple query. So a single query will find you the closest node match, and it basically backchains all the rules that I just spoke about. So in this example, we have our input species Ursus americanus, which is over here. It's basically a taxon name entity. It has our input name, and it's from the US. And then we have another entity node, taxon node, that we want to return, which has all its attributes. And these two taxon entities basically form a closest node relationship. So we're going to return the closest node. And as you can see here, it's up the tree at the order level. We're going to say, you don't know what this, you don't have this data, but we know it's of order carnivore. And as Andy was alluding to before, why would the UK have this missing data? So historically, the UK scientists, they classified everything based on visual observations. But now with the advent of DNA sequencing, you can identify bacteria in soil that you can't necessarily see. So those areas of the graph are kind of missing. So obviously you can see a bear, but we're just sticking to our simple example here. But now that you can identify the closest node, the researchers at Natural History Museum, they can consult experts and they can start to actually just build out this part of their graph. I think that might be neat.
Thanks, Siobhan. So we had everything now in place, the schema and what we were going to do for modeling. So what we then had to do is just change slide, load it into the graph database. So in total between the UK and US, we had about 2.5 million kind of entities and about 5.5 million relationships between them all. And so loading these kind of, there we go. There we go. So loading this in was a little slow, took about 20 minutes. And that's writing it into the graph database. We've got our cuddly bears here. And then, you would do your equivalence lookup to see what was going on. Now, for a few reasons, we decided to Dockerize all of this into what is can be called as a baked data pattern. There we go. So here we loaded in both not just the TypeDB server, but also the data so that it was all in this Docker container. So it could be loaded up when it was required and deployed as many times as needed in the same type of format. So there was a few reasons to do this. Taxonomists wanted to know what version of the taxonomy they were using. And the US one gets updated daily, while the UK one is a bit slower. And so they wanted to timestamp when it was used. And so this was one efficient way of doing it. It also meant we could pay less on server costs and things like that, which is another useful thing. The researchers have to do lots of equivalencing, but it is a bit ad hoc in nature whenever they get back from a research trip with soil samples and things like that. So we this is the sort of pattern that we used and works pretty well. So, 20 minutes to load into here. But once you've Dockerized it, you can start the container, even though it's got all those, the server and all the data in it in about 30 seconds. So it's quite quick.
Cool. And then for basically, we deployed this as just an MVP. So this is the initial architecture that we used to kind of get it working. Okay, I think that's just right. So basically, the taxonomic equivalence engine was deployed as a custom SageMaker instance using a lifecycle configuration. As you can see here, you've got the baked data image, which has not just your TypeDB server, but the entire database, the taxonomy of the trees. And this will get like basically pulled into your SageMaker instance so you can run the database. The actual equivalencing engine of the queries was available as a Python library, so that will just be pip installed into your SageMaker instance. And we also just provided a template Jupyter Notebook so that they could easily run the queries and also like look at their data. And this also does allow, it's actually quite easy to pull this down onto your local machine because this has everything you need. You don't need to install TypeDB and a simple, small like Python library, and you're up and running.
Sure. So essentially, because of this, the researchers now can pretty quickly equivalence all their DNA barcoding results and then load them up into the wider data ecosystem for study, testing hypotheses against other acoustic and visual observations. And so we were pretty happy with that. And the head of the Biodiversity Centre at the Natural History Museum thought it was pretty good. And so now they can do what took them a day previously to go through all their sample and equivalence them and check them. They can do in 10 minutes now. So it frees up time to do other cool stuff. So in summary, like naming things is still hard. Like it's almost a human problem, but knowledge graphs can help. And we found that the TypeDB and just, I guess, any graph database requires a bit of upfront data modeling. And actually that is really useful to fully understand your domain and data better. It's certainly an iterative process. I think it took 9 or 10 tries to end up on this model. We kept, turning up to the NHM taxonomists and scientists going, I think we can put everything in this way, and always add an additional kind of thing they wanted to add in and things like that. So it took a little while. It can also help with data quality. By loading things into the knowledge graph, we actually found things which didn't have parents, and it was a problem in the source database that they could then go and correct as well. And it can also, like Siobhan showed, quite nicely and quickly uncover new links in the data. So that's pretty nice. And so while this was, quite a specific taxonomy problem that we were trying to use knowledge graphs for, you can imagine we alluded to the main data management and get a 360 customer view. We use knowledge graphs for that, perhaps recommendations. And more recently, people have been thinking about using knowledge graphs to ground large language models, LLMs, for generative AI, because whereas vector databases and search may get you into certain areas of space similarity, knowledge graphs have explicit facts. And so if you can feed that back into a large language model, you might be able to add an extra layer of knowledge to that, which is actually correct and it to be the truth. And so obviously it was a combined effort building this. We had really close links with the Natural History Museum team, particularly Chris Riper, who was their expert taxonomist to build this. We had loads of great input from other thought workers on the project, and we were working with AWS, and Nishant Casey was their solutions architect, who was really instructive and helpful. I think that's it. But thanks, everyone.